So zoom in the background.
All right, so we'll go ahead and get started. Today we are very pleased to welcome Laura Amaral. She got her undergraduate degree and her master's in physics at Federal University of Rio Grande, Brazil. Her PhD in astrophysics at Universidad Nacional Autónoma de México. And she studies star-planet connections, in particular, stellar activity impacting atmospheric escape of exoplanets. And today we will hear about the effect of flares on the atmospheric escape of terrestrial planets. So,
Thank you very much, Allison. Thank you everyone to be here, listen to me today. And thank you for the invitation also. It's my pleasure to be here. The campus is amazing, so pretty. I love it. It's cooler than Phoenix. It was pretty pleasant to walk today. So yeah, today I'm gonna show you a part of my work that's basically understand how activity, the stellar activity can impact and drive atmospheric escape in terrestrial planets. So basically what I want to explain to you here today, it is, do stellar flares actually matter or not? Okay, that's the big question here. So first of all, I have to define some stuff so we can be on the same page here. So the first thing it is, what is a potentially habitable planet? So in this work, what a potential habitable planet it is a planet that has iron core and a silicate mantle. It's a planet that has atmosphere with enough atmosphere to have pressure, temperature to keep the water liquid on the surface. And this planet has to be in the habitable zone of the star. Another thing it is why we choose M-dwarf stars to explore the parameter space of how stellar activity impact and drive atmospheric escape. So basically, for those who don't know, this type of star makes 70% the stellar population of our galaxy. So there's a lot of M-dwarf stars outside. They expect that at least half of those stars has a terrestrial planet in the habitable zone. And 27 of 29 of considered potential habitable planets are planets around M-dwarf stars. So this type of stars are really important. However, the M-dwarf environment can be challenging for terrestrial planets. So basically what happens is a planet that today we are seeing that in the habitable zone starts outside of the habitable zone around M-dwarf star. So what happens it is we have here the planet in the pretty orbit here, and the habitable zone is far away off the star. So during the priming sequence of the M-dwarf stars that takes several millions or billion years, this planet is already formed there, but is exposed to high energy environment of this type of star. So here is an example of Proxima Centauri, that is M-dwarf star, the closest star of our system. So if you can see here, high energy radiation, that's basically XUV, that is X-rays plus ultraviolet. It's the flux is bigger than the flux that is incoming in the Earth in the present day. So this XUV can drive dissociation in the atmosphere of those planets and also heats up the atmosphere. What happens with the habitable zone of every star, it's the luminosity of the star change over time. So the habitable zone changes the position. So what happened, it is a planet that starts outside of the habitable zone, with the time ends up inside of the habitable zone. But the problem it is, by then, after billion years, was the environment of the M-dwarf stars are so challenging, a lot of radiation heating up the planet, that maybe the planet already have lost all the atmosphere. So the idea here is to understand what is the role of flares, because quiescent emission of the stars also emits XUV. But the thing with the flares is the XUV of flares, it's adding more chaos to the problem. So here's an example with the sun. The sun, everybody knows, it's close to us, really important. So For the sun, the flares that are have high energy or considered super flares, that is about 10 and 32 ergs of energy. They happens once or twice per solar cycle. That is basically twice for 11 years, 10 years mostly. And here's an example for last week. We have not such a big flare happening in the sun. Was class M. It's the flux is it's smaller. This scale is in log scale basically. So it's not a super flare. For which here super flare has to be like the flux has to be bigger. It doesn't happen like every time. So basically, this is how the sun looks like this week. And this is a gift for the event, just to contextualize. But for M-dwarf stars, those type of flares, the super flares, happen every day. So imagine every day receiving a huge amount of XUV radiation in the planet. And the planet is close into the star, so the same amount of radiation that a planet could receive in the position of the Earth that is far away from the sun, it's higher because you're closing off the star, because the habitable zone of M-dwarf stars are closer compared to the sun. And here's again 2 gifts for real flares, but you only have some pixels because we don't have enough definition. So it's a big difference between the sun and this. But basically, there are also flares. There are more than flares. There are super flares. This is a flare that's 10 at 34, and this is a flare that was 10 at 33. So the big question here is: do stellar flares actually matter for rocket planets? So what we did, and I did part of my PhD on that, was calculate the loss of water and primordial atmosphere of terrestrial planets around those type of stars. So I use a code where I'm a developer on it. The name is vPlanet. So basically, vPlanet has a lot of models. So people that work with geo stuff and exoplanetary stuff and stellar evolution, you all can use the same code, because what we do over there is combine different physics to make a big picture of the system. So we can coupling the interior of the planet, the stellar evolution, the atmospheric escape process, the orbital parameters, everything in a lot of simulations. So here what I did was consider one, the evolution of the luminosity of the star. Another thing was the escape process of that may happen in these planets, and add flare frequency distribution, but it's like the flare rate over time, changing over time. Because when we consider flares in simulations, you basically do that constantly over time. That's not accurate, because when you consider constant over time, you're overestimating the amount of energy that's arriving in the system. So what we did, it's using a model that basically tells us how this flare rate drops over stellar age. And I'm gonna have update that pretty soon, I hope so. So be tuned. So the atmospheres of the planets that I work with, it's basically a primordial atmosphere. Here you can see all those processes happening here. It's basically 3 processes that are gonna switching depending on the conditions. The first one is when the planet heats up so much, it's so close off the star that the star starts to drag off the atmosphere of the planet, strip it off the atmosphere of the planet. That is the Roche-Loeb overflow. Another option it is when the planet has when the flux in the planet reaches a certain limit, a critical limit. Basically, what happens is you start to photoionize the hydrogen in the atmosphere. So basically, the hydrogens that have enough energy to escape off the planet, they're gone. So you start to lose the atmosphere. Another option is similar, but in this case, you can recombine the hydrogen nucleus with the electrons that are lost in the atmosphere. So we ended up losing less atmosphere of that. So basically, the code is switching automatically between those 3 to be more accurate. And another option it is for surface water escape. So basically, after you lose all the atmosphere, the primordial atmosphere, we're not going to have atmosphere to keep the water liquid in the surface because you don't have enough pressure to keep that liquid. So what happens is the water gonna go to the atmosphere, and it can be again photodissociated. So what happens is similar. You're gonna dissociate the water molecule, and you're gonna again lose the hydrogen. When the hydrogen escape is like a river of flow, basically drag away also the oxygen. So you can also lose oxygen in the process. So here I divide my results in two. The first one is the primordial atmospheres, the second one under the surface water. The primordial atmospheres one, it is try to don't share too much here for now. I'm about to submit this paper, but just to like don't get too many spoilers. So basically what I did was taking the ionic system. There is a system that has M-dwarf stars and a lot of closing planets, a really young system. There's the age of the system is 23 million years, and try to use that as a case study to understand how primordial atmospheres can be lost by flares because the planets are too close. The star is really young, so those planets are in the beginning of the process of this atmospheric evolution. So basically what I show here is the system. We have ionic here in the center, have all this green area that I showed you is the habitable zone of the star. So all the planets are pretty close in. And what we see in the simulations was basically that the only planet that lose the primordial atmosphere within about 23 million years old, or what I mean by that is basically right now is about to lose all the atmosphere, it's only the terrestrial planet, that is ionic D, it's the blue one here. And the other two planets that are Neptune-sized planets, they don't lose the atmosphere. But if you see here in this plot, there is no significant changes between using considered flares or no. So that means that my work is doomed and I don't have a job anymore. No, let's try to figure out what is the parameter space that we are interested here. So, why that happens? So the planets are closing in, the system is young. Oh my gosh, I'm gonna lose my job. So I took the ionic D, that is terrestrial. The terrestrial planet has a lower gravity because it has a lower mass, and try to put this planet in different, no problem, different positions. So basically I keep the same star, and here is the orbit that the ionic D should be. This planet doesn't transit, it just have radial velocities. So it was attacked by TTVs. So basically this is the estimated distance. So, and I move the distance of the planet for different situations. I put the planet 10 times closer. I put the planet and the Earth equivalent distance. That should be the distance that the Earth should be around the star proportionally. I move this planet to 4 times the observation of the observed position, and also 10 times, and I play with that. So what I saw it is, okay, here we go. So if the planet is too close in, it's the dashed lines here. Basically, just to contextualize, this is a plot that is showing the hydrogen enveloped mass changing over time, okay? So the dashed lines here doesn't show any change. So that's because the planet is too close in. And when you move the planet a little bit farther in the habitable zone, that is the continuous lines here, we start to see a change that is about billion years of difference that we can drive atmospheric escape before just the quiescent emission. And you move a little bit further, only flares are actually, only adding flares to the system is that you actually can drive the complete atmospheric escape from the primordial atmospheres. And when you move farther away, that's almost like, again, you don't have any difference. So basically what you can see here, it is, if you put too close, quiescent emission is enough. So no problem. I mean, there is a problem. The planet can lose the atmosphere, but the flares don't actually matter. If you move too far away, there is just like not enough flux to drive the atmospheric escape because it's too far away. If you remember, flux just changes over a distance by the square of the distance, one up on top of the square of the distance. And when you put like in the middle point, like in the habitable zone, for, I don't know, lucky, grace, I don't know how to call that, but for coincidences in the habitable zone that the flares are matter here. So when you put here in the habitable zone or in the farthest part of the habitable zone, just in the outer part, the flares are so important. And they're important by a bunch of billion years. 1,000 years, sorry. So flares will matter, at least for planets that are Earth-sized planets, like AUMT, in the habitable zone of all early type M-dwarfs. Okay, because if you see here, this is not 23 million years like it is unique age right now. This is older. So older planets, when I'm talking about, it's a billion years, like TRAPPIST-1, Proxima Centauri. They are not the same star, so we have to be careful doing like the conclusions about that, because different star sizes gonna have different flare rates and gonna have different activities. But that's a good like initial guess. Okay. Now the surface water, that's more than published. You're free to go. So first of all, I'm gonna show a nice way to understand my plots, because they get like, I'm a neurodivergent person, so sometimes only me understand my plots, and I try to translate that for you. So try to follow up me. If you can, just stop me and I'm gonna answer your questions. So here I'm showing to you it is how the surface water changes over stellar age. So here you can see that in some cases dropping, because you have the fluxes incoming the planet and the planet lost water. So here's in bars, but for people that like terrestrial oceans, it has also the option here, so it's about 2. The dashed lines are when you add flares, and the continuous lines is when it's just quiescent emission. And here you have 2 sides of planets. The red ones are planets that has about the Earth radii, and another ones are super Earths at 1.5 Earth radii. So you can see it is when you have less gravity, you lose more water, because it's just easier to lose water. Now here comes the math. So basically what I did was several of those simulations that I showed to you in another plot, and I picked the last value of the simulation, but I mean that is the result here and here, and I subtract the amount of water that the flares can escape plus the quiescent emission from the quiescent emission only. So in this plots here, what I showed to you is only the contribution by flares. So the colors, it's the absolute values of water escaped by flares. So here in the vertical here, you have the stellar mass, and the horizontal axis, you have the initial water content. And if you want to go further, you have counter plots just to show you the percentage of water that got escaped, compare when the cases when you don't consider flares. So what you see here, it is, you have 2 cases also, sorry. You have 2 cases also of simulations. One the runaway greenhouse phase, it's across the whole evolution of the system, that in this case is a 1 gigayear. And another case when the runaway greenhouse phase is only during the primary sequence phase, that's basically when the planet is outside of the habitable zone. So the worst scenarios here is when you lose water in these regions that are darker here, basically. There is about 1.4 terrestrial oceans. So here what I can see, it is, 1 second. So in the left side, you're gonna have less flare impact. They have like lighter colors. So it's not, doesn't mean that the plants doesn't lose that, the water only means that the flare doesn't matter too much to drive the water escape, because the quiescent is enough. If you look to the other side, you can see they have white regions here. That means that no water was escaped, but it's because the planets are too big, so the gravity prevents that. But there's some cases that even if the planets are too big, they are around of stars that are like less massive. less massive stars, M-dwarf stars, they're more active. So here, in these cases, the flare is going to be important because the quiescent emission is not enough to drive a water escape in such a higher gravity planets, but the flares are. So yeah, basically what I'm saying to you is super Earth's going to be more affected than it's this cases here. And planets that has the Earth size, that is this case here, they're going to lose up 1.4 terrestrial oceans. To go further, I knew my the people that are gonna attend here, they're like also gel people. So I add oxygen because there's a lot of people that do this gel stuff and exoplanets that they love detection of oxygen. So what I did here is basically plot the amount of atmospheric oxygen in the atmosphere because of water photolysis. So that doesn't mean that we're gonna see, I don't know, 300 bars of oxygen in the atmospheres. Only means that this was the amount produced by the flares, basically. So the white regions is basically here when the flares doesn't make any difference. So it's about the same amount of oxygen building up in the atmosphere because of quiescent emission. The red regions is the exceeding amount of oxygen building up in the atmosphere because of flares. In the blue regions, it's when the escape of water was in the photodissociation was so much that we could drag oxygen from the atmosphere. So we have like negative values compared to the quiescent emission. And these regions here, you cannot drive water escape. So you cannot drive water photodissociation. You don't have any oxygen building up in the atmosphere. Okay, so I'm about to finish. So the takeaways for this talk is basically super Earths can maintain water in the surfaces, even that they are around active stars. Also, stellar flares impact more the water escape in super Earths in mid to late M-dwarf stars, so here in this region. And another thing from the beginning of the talk, it is the stellar flare is going to be important for Earth-sized planets in the late stages of evolution if they are in the habitable zone of Earth-type M-dwarf stars. It's pretty specific because the simulations are pretty specific. So right now what I'm doing is exploring the parametric space to tell you actually, imagine like a map of where flares matter or not. So I'm building this map right now. So that's it. Thank you so much for your attention. And I can take questions right now.
So are there any questions in the room or online?
Thank you. Really great talk. Really cool stuff. I'm curious if V-planet model, does it also model like outgassing from terrestrial planets that could replenish an atmosphere that's being escaped? Or how does that balance come into play?
It does. We have the interior model, so we have outgassing. I'm not sure the species. I think we have CO2 and we have some water too, like for like a secondary atmospheres replacement. That's another project that I'm doing. I'm not doing outgassing, but I'm working with people that do outgassing, so you can build like the system like from inside to outside and have the whole the complete system evolving, if that makes sense. But yeah, it does.
Cool. Thank you.
Super.
Hi, I really enjoyed your talk. I was wondering if you could tell me a little bit more about how you go about estimating the mass loss rate. In particular, there's been some work from some Japanese groups recently, which points out that photochemical recombination as well as atomic line emission may cool the atmospheres of planets exposed to intense XUV and calm their escape rates. And I was wondering what you thought of this and or if you've considered this.
No, actually, that's another update we have to do in the code. Like, that's a really good thing. Thank you for the question. We really have to do the cooling process in the atmosphere. You don't have that right now. There's a lot of things we didn't consider, like the interior evolution, like you're saying, and the outgassing replacing the primordial atmosphere. I could not do that because I only have 3 years to finish my PhD and I have so many parameters. But you're totally right. I don't consider that. Let me see if I found the. Yeah, but like you're talking about to have another model that besides of the photo dissociation. I have so many slides. I'm sorry. Besides has the photo dissociation, also consider like the cooling, right, in the atmosphere. Yeah, we don't have that, but I know there's another people. The code is really big, so there's I'm in charge of flares. There's people in charge of interiors. There's people in charge of another thing, and another doing that. But yeah, it's you totally have to do that, especially when you're doing like secondary atmospheres and the CO2 building up. So you have this like, we start to heat, but if you put too much CO2, it starts cooling the planet, right? Yeah, and yeah, that's definitely we have to add that, but it's not here right now.
Anna.
Hey, great talk. I had a question about what you're assuming for the dissociation of water in the atmosphere. I guess my question would be, in your atmospheric escape model, are you just assuming that all of the water has dissociated in the upper atmosphere?
We have an efficient parameter, so not all the water gonna be dissociated, because like this is disclaimer. This is a model that is some people call it like a box model, is a 1D model. So the good thing of this model, you can run like several simulations, like 88,000 simulated in 3 days. The bad part it is you lose resolution because it's not a 3D model. So what we did, it is basically understand that you're gonna have an efficiency to lose and dissociate the water, so you can regulate that. And we use a model called Beaumont from Beaumont 2017. It is basically regulating like the efficiency by dissociating of water and because of XUV. That answer your question?
Yes, it does. Thank you so much.
Thank you.
Are there any more questions in the room?
Question online.
Yeah, there's
Yeah.
another question online. Manly, do
Okay.
you want to ask your question? Or I can just read it. If you have a mic, please ask yourself. Okay, I just read it. So for the mass loss rates, are you using them tidally adjusted mass loss rates? For example, from the Erica paper you cited? If so, which is the more impactful, smaller tide gravity or higher stellar activities with M-dwarfs?
That's a really good question, because you have to consider circulation, right? Like if you're tired, yeah, since we are 1D, we consider there is a tide parameter for our model, but we keep that constant. And besides of that, the orbital parameters that we change in the system, they're like they don't change over time. We keep that fixed. Like the planet, it's not losing angular momentum for any reason, and you're not changing the ephemerides of the planet. So we keep that constant. But yeah, that's another thing we should consider in the model. It's tightly lock the planet tightly to the star, because after a certain distance from the star, you're basically gonna have that yes or yes, especially for M-dwarf stars, planets in the habitable zone of M-dwarf stars, mostly gonna be tidal lock. So yeah, we consider parameter for that, but we don't have the full evolution of the orbital parameters for the tidal lock.
Do you examine a range of different initial atmospheric compositions? Do you find that matters for escape rates, or you just assume initial composition of an atmosphere specific qualities?
Yeah, you mean by the amount of atmosphere?
Yeah, like ratios of oxygen, carbon dioxide, water.
Yeah, so okay, this for the primordial atmosphere, no, because it's just hydrogen / helium. For the surface water, we just consider that doesn't have a secondary atmosphere from the outgassing yet. So this is something that I'm implementing in the code. I don't want to give spoiler because I don't have the results, but knowing my code, at least with this type of code, I think gonna have difference because the efficiency of escape gonna be changing because of the cross mass between the species. So some species are gonna be heavier and gonna be able just be lost by non-thermal process. In the meantime, another species is gonna be really lighter. I don't know if you have methane and produce hydrogen, the methane gonna be dissociated, maybe gonna be lost by hydrogen escape. So yes, it's gonna change. You're gonna build up more stuff. You're gonna recombine other stuff. Oh my gosh, this is another thing that I have another collaboration about that. But yeah, we can have like photochemistry, like the atmosphere of the planet gonna always try to find an equilibrium. But if you have activity, maybe the equilibrium is because of a basal activity. Like, or maybe it's because the flare is heating up the atmosphere and is messing up with things until you have another equilibrium state. And of course, it's gonna change the escape, the type of escape and type of species over there. That's not my work. It's somebody else's work that is a friend of mine. He's working on that. But yeah, long story short, I don't know how gonna change, but I'm pretty sure they're gonna.
Can you put like a bow on what your conclusion would be for the chances of finding like Earth-like planets with water that would be habitable then on a long-term time scale?
Okay, so I'm gonna play the devil advocate because what I try to do with the simulations is basically to push the system in a really resumed way, because I have a lot of things I'm not considering, but also in extreme cases like super flares. I'm not considering normal flares here, it's just super flares. So these results we can interpret like a upper limit, like a educate guess for upper limit. So what I expect it is that we have less water being lost, but only in the cases that we have a secondary atmosphere. So because here I don't have anything to protect this water. That makes sense? So if I put a secondary atmosphere on top, things gonna change, chemistry gonna happen. Maybe they're gonna help to, like, I don't know, maybe gonna build up ozone layer and you're gonna absorb this ultraviolet and you're gonna prevent that. Or maybe in these cases, the planets are too close to the star that it doesn't matter, because you're gonna lose by not just by flares, but maybe by interaction with particles from the star, like CMEs or CIPs. So there's a lot of things that has to like goes on that are not considered here. But what I think is happening, it is for terrestrial planets, after just a little bit of million years, not too much, like tens of million years, no primordial atmosphere. And the planet is active enough to replace the secondary. Maybe we can see something, but I don't think it's gonna be too thick. Because I have a lot of, especially if the planet is too close enough to the star. Yeah, but yeah, like but in another place like super Earths and sub Neptunes, you know, they're just like easy to go. They're not rocket science because they have more gravity. So in the worst case, you still have something over there. I don't work with Neptune, so I decided not to going too farther over there. But my guess it is, if you have to pick one planet to see any atmosphere, should be the more massive ones for different reasons. One, it's because it has more gravity, so it helps to keep the atmosphere more time, but also because the signal to noise ratio when you have the transit is just bigger because I have a bigger planet. So there's a lot of, I love terrestrial planets, but they're hard to they're rocky hard to get data. So yeah, but cross the fingers that we can observe things with JWST right now. With yeah, I have faith. My basically is that. And then that answer your question.
Yes. Are there any more questions in the room or online? Okay, I think we can go ahead and end a bit early today. For those of you who are physically in Tucson, we are going to go to lunch with Laura today. There are a few spots left for lunch, so if you want to come to lunch, come see me right now or send me an email right now.
Thank you
All
very
right.
much,
Yeah,
everyone.
thank you.